Okay, it's 6:30 and I'm finally getting to studying the night before the test. This is the beauty of my procrastination. The house now has more apple fritters than we could eat in a week. My paintings are organized so that the canvases won't get damaged. My bedroom is cleaner than it's been in the past 2 months. And, yeah. Oh, got the dishes washed too. I'm finally sitting down to try and get this homework done, or this studying done. Anyways. So, I'm going to start with homework number 4. Problem 4.57. This is a very simple one that really just explains the material derivative and what its purpose is. Okay, so this is 4.57. A gas flows along the x-axis. So if we were to look at a streamline, it would just simply be x. Along the x-axis with a speed of v equals 5x meters per second squared at a pressure of P equals 10x squared newtons per meter cubed. No, sorry, that should be squared. Meter squared. Yeah, that doesn't make sense. Where x is in meters. A, determine the pressure, determine the time rate of change of pressure at the fixed location. B, determine the time rate of change of pressure for a fluid particle flowing past that point, x equals 1. Explain without using any equations why answers to part A and B are different. Alright, let's start with A. It's the real easy one. If, well, pressure is in terms of x, not t. X is not a function of t, not so far as we know. So if we're just looking at this point right here, where x equals 1, and we've got the fluid flowing past it, flowing along, it's not really doing anything to the pressure here, because the pressure is changing with location, not with time. So at a given location, the pressure change with respect to time, the partial derivative of P with respect to t, is the partial derivative of 10 times x squared, which is 0. It's not changing, having to do with time. Alright, now I wrote the same thing down here, but I pointed out that it's for the particle. That's actually not 100% accurate. We don't want partial derivative, we actually want the material derivative. Okay? That's what these capital D's stand for. The difference between a material derivative and a partial derivative is basically the material derivative looks at the whole thing. X is not necessarily a function of time, and time is not necessarily a function of x, but P can be a function of one or both of those. So, what the material derivative does is it actually looks at both the effects of both time and position, even when they're not directly correlated, even when they're not directly functions of one another. And the way it does this is by saying d whatever, dt, equals the partial derivative with respect to time plus u dp dx. This is the derivative of the x component of velocity. This is the x component of velocity times the derivative of p with respect to x, plus basically the same thing, the velocity in the y direction times the derivative of p with respect to y. I'm actually doing regular derivatives. These should be partials. Alright, so our velocity field actually looks like 5x, because we know we're moving along the x-axis. That's given. It doesn't necessarily have anything to do with the position of x. You could technically have a vertical movement that would change with respect to x. That just means that right here it's going to go vertical at a constant speed, and right here it's going to go vertical at a different constant speed. But it could still be a function of x, even though it's the velocity in the y direction. Alright, but we are told that the gas is flowing along the x-axis. So all the velocity is on the x-axis. So that means that in our y-axis we have no movement, in our z-axis we have no movement. So this is u. This is v. This is w. These are 0, 0. There's nothing to be had there because v and w are 0 themselves. The partial derivative with respect to t, if we look at this, we already know that's 0. Alright, so we wind up with dp dt is actually only considering at this point the velocity and the change in pressure in the x direction, and that's because that's the only that's all that's happening. There's no change over time, honestly. Like the particle will move over time, but that's only because it can't travel instantaneously. There's no real change that comes just because of the time difference. All the change is really having to do with the position difference. Okay, so this is 5x times dp dx, so the derivative of this with respect to x is 20x, which equals 100 x squared. X is at point, this is looking at a particle as it is at point 1, while it's passing point 1. So at point 1 in particular, the change in pressure is 100. I imagine this would be newtons per meter squared per second, which should be a multiplication sign. Yep. Alright, now we're going to explain the difference. Why are they not equal? Well, if you look at this particular point, there's no time change. The particles flowing past this point are going to be producing the same pressure if you wait here for 1 second or a million years. However, dp dt does not look at the point. It looks at the particle. So if we were to, saddle up a particle and try and ride it past this point, we would feel a change in pressure. It would be low pressure over here because x is small, and as we travel along x, pressure would get greater. And that's why these two are not equal. The partial derivative with respect to time looks at a particular point, and there's no change there. But the material derivative looks at the change on the particle. And that's basically our answer. What he wrote is, for this steady flow, the pressure at a point is constant, part A, but the pressure for a given particle changes with time, part B, because the particle flows into a higher pressure region, which is basically what I said, but with less colorful language.